Okay, hi, Brian Harrington here again. We're continuing on with our automotive simulation guide. We just had covered the design phase. Now we're going to be stepping into the operational decision or the operational procedures phase. And this is where once we have implemented our design and we've got the plant actually launched and up and running, often we're going to be looking at what's the best way to actually run this plant. You know, we can step into looking at the shift patterns and different operating rules. So this is where we're going to be spending a little bit of time looking at some of the operational decisions. So operational procedures, like I stated, is once the facility has been launched, we're up and running, we're going to often see quite a few different, our objectives, our overall set of objectives might shift a little bit towards looking at how our market demand, when it fluctuates. So we might say that if we were building some convertibles, once summertime approaches, we're going to be seeing on our facility that we're going to be possibly running more convertibles, and so we'll have some differences in our take rates. So this definitely touches on the mixed model assemblies. So we're going to see that more than likely this facility is going to be running different vehicle types down the same assembly lines, you know, exercising flexible manufacturing. So we might be producing 2, 3, or 4 different vehicle types. And so obviously there's going to be some operational and different release rules of building a set of or the mix of vehicles and the release patterns on how we do that. Even just looking at the shift patterns in labor itself. So touching on when we have morning breaks, lunch breaks, afternoon breaks, so the operating patterns. And once we have the facility up and running, we know that bottlenecks can occur, and the bottlenecks can actually move around the system. So how can we protect and get procedures in place to minimize the effects of bottlenecks? So let's go ahead and step into looking at some of these objectives. And before we do, we'll look at an online, this was from the Ford Motor Company's online magazine, and it just shows by 2017, which we're currently at, that Ford on average is producing 4 different vehicle types in each one of its facilities. So the days of just building one vehicle type per plant is pretty much in the past. So now we have less overall manufacturing facilities, yet our family of products might be even growing. And so we're definitely using the flexible manufacturing and the mixed model assemblies, and we're doing more with less. So our facilities are becoming more complicated, yet we're able to pull off building, we could be building a sedan and a pickup truck, for instance, on the same platform, and we very well could be looking at this facility running 2 to 3 shifts. So the wiggle room of producing lost units via overtime is definitely minimized. So it really puts the pressure on when we're trying to meet our targets to get it done within the allocated shifts, because we very well could be running, like I say, close to 24 hours or full shifts or full capacity at that particular plant. So when we look at how simulation can improve our key operational objectives, we're going to be looking at this facet of mixed model assembly, building several different vehicles down the same assembly line for through flexible manufacturing. Often it touches upon our actual build schedule. So are we going to batch build? Are we going to be building to order? And often it is a combination of the two. So optimal operating shift patterns is key also, and optimizing the staffing requirements and utilization. So when we look at optimizing for mixed model assembly, we're building different vehicle types on the same line. So in this particular instance, we might, within the model, have 4 different vehicle types. In this case, we're using a probability profile distribution. We have 28% of vehicle type 1, 34% of vehicle type 2. We have a low runner, 9% of this vehicle type 3, and finally 29% of vehicle type 4. So when we do that, that obviously increases our overall complexity of the facility. And we might have unique dimensional control equipment on each one of these platforms. So when we talked about a palletized loop, are they going to be, can these vehicles all be produced on the same platform or the same pallet? And the answer might be yes, or this low runner might require its own unique pallet. So that complexity in itself becomes large on just managing unique pallets within a palletized loop. It could become very complex, particularly if we're building to a customer order. And each one of these vehicle types might have unique cycle times. So, you know, we talked about in the design phase coming up with optimal line rates and station work cell rates, and balancing manual and automated operator, or manual and automated cycle times. How is that going to affect us when we're looking at each one of these vehicle types having a unique set of cycle times for both automated and manual? So the vehicle sequencing and scheduling obviously becomes very key to the overall performance of the system. And when we have additional vehicles in our family of products, this is definitely going to increase the overall line side racks that are key for our sub-assemblies. So when we look at a set of vehicles, in this example, we have 3 different vehicle types, and not all like we just discussed, not all vehicle types are equal. They're going to have different cycle times, require different subcomponents. So scheduling is very important and requires usually quite a few different what-if scenarios. So what is the best build schedule? Often we try to build to a customer order, keep it close to the customer order as possible. And if we have a low runner, maybe vehicle 2 has a much, requires a greater cycle time. That could cause potential throughput losses for vehicle 1 and 3. In other words, vehicle 2 would be pacing the line. So we might want to test out, if we do have a low runner, maybe possibly building that in small batches is going to be the best, or possibly coming up with some blend of vehicles, or potentially just different release rules. In other words, we might say never release more than 5 of our low runners in a row. So coming up with different scheduling rules often becomes a very, very complicated without a simulation. And if you were trying to do this deterministically, it's going to peter out very quickly. So in the simulation world, we can really test out various build schedule patterns and sequence, and look at our overall sequence, and we can come up with what is the most optimal release pattern that comes that that gets us close enough to our original customer order, but also achieves our overall throughput targets. So once we do have the facility up and running, and we're achieving and we're looking at achieving our overall throughput targets, we want to look at our operating patterns. Are we going to be running this facility within 8 hours? Are we going to be looking at 10-hour shifts? Are we going to be releasing our operating force with a tag versus a mass release pattern? A tag situation might say if a particular operator is going on break, then another operator comes in and continues where he left off, with where he or she left off. So we're going to continue the operation. In other words, there's really no stoppage. Where a mass relief pattern, all operators, or at least a subset of the operators, will go on break at a particular point in time, and the facility will actually go down for those, maybe 10 minutes or for 20 minutes for its lunch time. So coming up with the optimal operating pattern, and even staggering different shift or break patterns within the facility that causes the minimal throughput losses when we're looking at an overall shift period. So that brings us to the actual detail of when we do have our operators placed in the various lines where they'll be working, looking at coming up with do we have a sufficient labor force in place? Can we find out where the sensitive areas in the system are? And what are we going to do to protect these sensitive areas? So are we staffed properly to handle our downtimes? Do we have our skilled trades and maintenance plans in place? Do we have sufficient material handling operators such as forklifts and tug drivers? And do we have our marketplace where parts are coming in or in subcomponents? And are they getting delivered in key time for those line side racks? So looking at our operators becomes key when we're trying to keep our facility up and running. So once we have our procedures in place, and we're trying to keep them to achieving our targets. So this comes to basically the old saying is, if you can measure it, you can manage it. So of course, good designs such as poke yoke design airproofing procedures are going to keep us to achieving our targets. But continuous improving and having a set of performance metrics in place is going to be give us the tools to make sure that when we start to lose throughput or have potential, when we're looking at our control chart, when we see that we are actually experiencing some low throughput hours and so on, how can we minimize those? So when we come up with a set of performance metrics, and this will be our next topic that we're going to cover, and that'll tie into our continuous improvement and tracking performance metrics along the way.